So it's not to remind you, it's basically just to make the starting point for the next lecture. What we've got at the moment, we've got a kind of general theory for radiation from relativistic objects, from objects with relativistic outflows. This kind of general theory involves synchrotron emission, inverse Compton scattering, and I told you that all this should be done in a good way. In QED, if you consider scattering, you have to take into account pair production, etc., etc., etc. And then you get a model which more or less describes, well, I shouldn't say this, more or less describes everything, but yeah, I gave you an example that not actually everything. But then, once again, to finalize, it was not a problem of the model itself, it was not the problem of physics, it was a problem of our simplified assumptions about geometry, most likely. But this is the best we can do at the moment. Let's try to improve on physics now, not on geometry. About geometry, unfortunately, we cannot tell anything specific, and probably it's too early yet. So, the physics is consisting of many interrelated subjects, and if you look at the theoretical iceberg, this is what we see, the radiation processes. This is what we discussed in the first lecture. And this is 10% of the iceberg above the water. The rest is hidden under the water. You don't actually observe it. It's a lot of physics. It's particle acceleration, many possible processes. It's the processes related to creation and decay of the magnetic field, including turbulence, whatever. And what's worse, actually all these blocks are interrelated both ways. It's not that you accelerate particles and this is the input for the radiation processes. It's not, unfortunately, like that. It's more complicated. Radiation processes also act on acceleration, and they change the way particles accelerate. Well, acceleration, I think you kind of probably have a feeling for that. Acceleration, that means changing the plasma content, the plasma particle content, of course influences the generation of the magnetic field, and obviously you need magnetic field to scatter particles to accelerate them. So it's like, again, it's both ways. Maybe the most subtle is that radiation may influence the magnetic field. It can, because what makes the magnetic field is the currents. Currents are made of particles, and if particles are radiating, they are losing energy. This is a dissipation process that also acts on the magnetic field. So it's all interrelated. It's too complicated for humanity. So the conventional approach to the situation would be like that. Let's try to consider acceleration as a standalone process, think about it, extract something from it, and then plug as an input to the radiation processes. So you do acceleration alone, then you take the result as an input for the radiation. It's not that, even in this simplified situation, it's not that much we can tell for sure. More or less, we are sure that all acceleration, all Fermi-like acceleration processes will result in a power law distribution of particles. But unfortunately, at this moment, we still have to assume the exact slope of this and even the exact shape of this distribution. But then we can speculate something more specific about the average Lorentz factor of the accelerated particles, for example. What can we do if we do not know anything? We can do energy conservation law. If there is energy coming to the shock, this energy is distributed between the particles, and some fraction of this energy, which is epsilon E here, goes to the accelerated particles. So you take an average energy per particle, you take the fraction of particles that are being accelerated, and this way you calculate the average energy of an accelerated particles as a function of, this is for a shock, as a function of Lorentz factor of a shock, and the proton mass comes here. This gives you an energy of a proton. The energy is kinetic energy of protons, of course, initially. This way you can estimate more or less the injection Lorentz factor. Well, we don't know what's epsilon E, we don't know what's psi E. The usual assumption is psi E is equal to unity, all particles are being accelerated, all electrons are being accelerated. This is an assumption from peak simulation, particle and cell simulation, plasma simulation. We know that it's more like 1/10 of all particles, but this is not quite certain. Epsilon E, the usual assumption is 0.1. Nobody dares to say that all the energy goes to accelerated particles. And yes, this is what we see in simulations, more or less, 0.1. Anyway, no matter what we assume about that, what we think about this is just a number. We believe that there is some complicated physics in the shock that provides you these numbers. We do not understand the physics completely, no problem. We just take it as a parameter in your theory. Then what you can say from this relation that the Lorentz factor of accelerated electrons is proportional to Lorentz factor of a shock if you accelerated the shock. This is a very firm prediction of this standalone acceleration. Then, if you consider acceleration in jets, then it can be everything. There could be that inside jets there are shocks, and then it's a shock acceleration just in a different environment. It could be, and it is, that the jet has its own velocity profile, and there is a velocity shear. Shear flow also accelerates particles. Unfortunately, for a shear flow, it's much more complicated, the acceleration process. And it's not so easy even to determine the slope of the injection function, of the accelerated particles, because you don't really know what's the properties of the scattering magnetic field. In this sense, you have to assume something about it. Oh, there is a lot of freedom here. There are many options for jets. So at some point, if I need something specific, I will talk about shocks, because shocks are better defined physical problems, so to say. It doesn't mean that in the jets you will have something completely different. No, you will have something similar, but more complicated in the sense of making an exact theory. What's the problem of acceleration if you have a relativistic shock? The usual assumption is like this. You have a shock front, and particles coming from the upstream to the downstream, they're being reflected from the downstream going back into the upstream, and because the upstream is faster than the downstream, it's like between the moving walls. You put a particle between the moving walls, it scatters back and forth and gains energy. This is called Fermi process. And this, we know, we see shocks from supernova remnants. We know that it accelerates particles. Moreover, the theoretical predictions about that are more or less consistent with what we see. For relativistic shocks, it's not that easy. I mean, to do this in a normal way, you assume that the particles are diffusing in the downstream. That means the downstream has infinite diffusion length, effective. But effective diffusion length actually depends on the speed of the downstream. If the downstream is moving too fast, and in a relativistic shock it moves with 1/3 of the speed of light, then it's not really scattering. The effective region that acts in your game has optical depth of only 2. 2 mean free paths of a particle. It's not really a diffusion problem. This is what was well understood by many people. Yes, all of you probably, or the majority knows the joke that a physicist easily calculates the problem of stability of a chair with one leg, of a chair with infinite amount of legs, and then spends the entire life to calculate stability of a chair with a given but not infinite number of legs. This is exactly the same situation. When there is infinite number of scattering, we know the answer. When it's just finite, 2 or 3 or something like that, it's more complicated, much more complicated. So what people, clever people, what they do, they say, okay, it's not just a scattering like billiard balls. it's a small angle scattering. So to change the particle direction to reflect it back, we need many, many, many scatterings. Again, it's an infinite number, kind of play. Once we have an infinite number, we can calculate the answer. The people have done it, and the answer is actually different from what we usually have for non-relativistic shock. Strong non-relativistic shock gives you 2. This is 20/9, slightly more than that. But nobody knows what are the scattering properties of the turbulent magnetic field. This is an assumption that you may use an approximation of small angle scattering. This is just an assumption to simplify your theory. Okay, what we can do, we run a simulation. We put many, many billions of particles actually into your simulation frame. All particles have charges. These charges produce currents. You use Maxwell equations to calculate from the currents to calculate fields. You use those fields to propagate particles using Lorentz force. So this way you simulate plasma. This is quite, I would say, quite time-consuming simulation. The very long simulations that are published actually are taking probably millions of CPU hours. This is really time-consuming. So every time someone gets a big grant to pay for the computer time, there appears a new simulation which is, say, 2 times longer than the previous one. And this is the last one that has appeared in the last, more or less in the last year. Okay, it's still the same. It doesn't change. The fraction of energy in accelerated electrons is still the same. The magnetization near the shock front, now you can consistently calculate the magnetic field. Magnetization, that the fraction of energy in the magnetic field is 0.01. Unfortunately, the magnetic field is short-lived. What does it mean short-lived? What does it mean short-lived here? I will specify later. But you see, it's a red color, so you have to pay attention to that. Okay, and what you see is that you start with distribution like that, and it extends. It's kind of developing a power law tail. This is what has been seen for a long time. The longer you run the simulation, the longer this tail goes. And well, the hope is that if you are in a possession of computer of the size of the universe, then finally you will get a power law tail to infinity, more or less. Nobody knows, because this is not enough to claim that you have a power law tail, but it looks like it starts to develop. What we have done recently, and I think the publication maybe has appeared today or something like that, we tried to reduce the computational cost in a sense that our simulation box now moves with the shock. It's not that you start a shock and it propagates through the simulation frame, so you have to extend your simulation frame in time. Now we have fixed simulation frame, the shock stands. It's not an easy task to do, but we did. And you see what happens. This simulation is several times longer than the previous one, than the longest. It's a different setup. It doesn't mean that we spend several times more CPU hours. No. You see what happens with the particle's energy. The average energy of a particle, you start with this. It quickly increases. This is Fermi acceleration. And this branch, it still increases, but at a different pace. It's not Fermi acceleration. This is just a selection effect. The particles that have the largest energy, they leave the simulation box at a slower rate. So you have kind of increase in energy, but it's not because particles are accelerated. It's because you quickly lose the low energy particles. So they stop accelerating at this point, roughly. You increase the energy by a factor of 10, and that's it. So Fermi acceleration in a relativistic shock doesn't work. This is the answer. Why? Well, this is the distribution of particles, angular distribution of particles, and you see what's going on. The particles are moving not from the downstream to the upstream, they are moving almost parallel to the shock plane. they are starved of a possibility to scatter. The magnetic field, short-lived magnetic field, it is contained in a small region, and it's not enough to keep the highest energy particles. So if you want to keep them, they know what to do. They have to move along the shock, so they have a possibility to scatter. But even this is limited. Now they stop accelerating. Do we have an alternative to that? Yes. Once again, it's not that you are inventing epicycles. You just start thinking, was the previous theory of radiation, was it complete or not? I told you that you have to include into this theory particle creation. Okay, if you create secondary pairs in an emitting region, you just add the secondary pairs to the ones that you already have there, and you recalculate radiation. This is what has been done. But now, photons do not know whether they are in the emitting region or in front of the shock. The emitting region is behind the shock. There, the magnetic field is the strongest, the particle density is the highest, the energy of particles is the highest, so this is the region where the radiation is concentrated. It's behind the shock. And this region has a boundary. What if photons go ahead of the shock and produce pairs there? It should happen, of course, roughly with the probability half and half. Later, I will try to follow the path that these pairs take and see what happens then. And we'll see that this actually gives rise to another acceleration process, very different one. But I want to tell you at the moment that there are several questions, like in the previous time when we were extending the synchrotron radiation into synchrotron self-Compton radiation, there was a question and several sub-questions that arise. Those ones were all solved. But now you see it's far from being completely solved, but we understand the major part of this situation. So coming to the process. We have electrons and positrons behind the shock. They radiate. They produce synchrotron photons, low energy, and they produce high energy inverse Compton photons. I told you already with just hand waving, that in principle, from what we see, we can guess that we are somewhere in between the Klein-Nishina and the classical scattering, and that means you are quite close to the pair production threshold, and this is the point where the cross-section has its maximum for the pair production. So you expect that if this is true, then this process is quite efficient. But let's suppose for a while that you have low energy pairs behind the shock. That means low energy synchron photons and low energy inverse Compton photons. That means you are below the threshold, more or less. And only very few photons will be above the threshold. Those few photons can produce very few pairs in the upstream. And the upstream magnetic field will catch up these particles and bring them back to the shock. But what happens, you understand, what happens is the reflection from a relativistic wall. Every such reflection gives you gamma squared. And remember that for gamma reverse, gamma is several hundred, so gamma squared in principle can be 10 to the 5, which is a huge amount. Okay, for shocks in jets or whatever happens in jets, this Lorentz factor difference is smaller, but still if you have gamma 10 squared, it's 100, it's a very large number. Saying that you do not produce many secondary pairs doesn't mean that you can neglect it. These very few pairs are multiplied by gamma squared. Few in this situation would be much less than 1 over gamma squared, which is really very, very few. And it's not the case. This is a spoiler, it's not the case. The opacity is not that low. Okay, now you have all the energy of the incoming flow, of the energy of the upstream, available to give this boost to the secondaries, very few secondaries. If you give a large boost to very few secondaries, that means every secondary particle would have large energy. if it has large energy, it produces high energy synchronous photons and high energy inverse complex photons. You're very well above the threshold. You produce pairs efficiently. Now you produce a lot of pairs here, but the upstream power is the same. If you have to distribute this upstream power over a large number of pairs, inevitably, every pair would have small energy. If you have small energy, you have small energy of synchrotron, inverse complex, etc., etc., etc. So obviously, it should balance somewhere, and it balances at the point where the absorption is more or less the maximum possible, or the maximum that is allowed by physics. Now, why there is a maximum of absorption? Why it cannot be, it's written here, it cannot be more than 0.1, where it comes from. It's not my will. You can try to solve the equation for a shock. What you do is that you assume that there is a shock. This is the downstream velocity, Lorentz factor actually, but this is a measure of velocity. You have the Lorentz factor at infinity, and then you have this precursor to the shock, where the upstream is slowing down because of injection of these secondaries that take momentum from the upstream flow. And still there is some subshock, which is usually called viscous subshock. Why viscous? Because it works on what we would call a viscous spatial scale, the scale that corresponds to the plasma viscosity, which is very small compared to the mean free path of accelerated particles. And now what you do is you solve hydrodynamic equations. I am not showing this. I am not going to go through all these equations, just the answer. You solve hydrodynamic equations for this situation, and you get two solutions. One is for the upstream velocity here at the viscous subshock, and another branch, the lower branch, is for the downstream velocity. If there is no feedback, this is the feedback, this is the fraction of energy that you send it to the upstream and have absorbed there. If there is no feedback, then it's just a normal relativistic shock, which you can find in the paper by Taub. This is called Taub-Adiabat. And if the upstream Lorentz factor is infinity, very large, then the downstream Lorentz factor is such that the velocity is 1/3 of the speed of light. You reproduce this. But once you start to increase this feedback, what happens is that the downstream velocity increases, the upstream velocity at the subshock decreases, and if you go too far away, you come to the sonic point. So the flow just comes through the sonic point without any subshock. It disappears. If the subshock disappears, that means that you will have troubles in injecting particles into the game. So you have to stop somewhere here. When the subshock is still there, maybe it's becoming subrelativistic, but it's still there. You cannot increase the absorption fraction too high. What about jets? Unfortunately, I don't have an analytic solution for jets. Jets are more complicated because there is one extra, I wouldn't say it's a variable, extra degree of freedom actually. You have to assume something about the transverse velocity profile of the jet, which is not known. This is another story, and it's very difficult to calculate it from the first principles. So I don't know what exactly is going to happen at the jet, but just to show you that the process itself is still there, consider a photon which comes from the side of the jet where the velocity is low. It comes to the center of a jet where the velocity is high. It produces a pair, and this pair gets a boost compared to this region where the photon was initially created. So this pair can create secondary photons. They can go sideways, and they also get a Lorentz boost because of the difference in the velocity. So it works in the same way. All you need is that between the point where the photon was produced and the pair was produced by these photons, between these points, there is a large relativistic velocity difference. This is all you need for this process to work. The only difference between the shock and the jet is that for a shock, we have kind of analytic theory, very simplified, but we still have it. For a jet, we don't have it. Only qualitative estimates. Now, just to figure out it a little bit different way, in a nutshell, what's going to happen if you have this balance at the shock pair balance? You have photons from the inverse Compton peak, photons from the synchrotron peak, they meet each other, and they also should satisfy the condition for the most efficient pair production. This is the way you increase this process, the rate of this process to the maximum. This is the condition. Oh, the product of these two energies is mc squared to the second power. We know what's the relation of the synchronous energy to the magnetic field. It's gamma squared times the magnetic field times some dimensional coefficients. The inverse Compton energy can be estimated as gamma squared times synchrotron energy. So it's gamma to the 6 altogether times the magnetic field. It comes in two places, times the magnetic field squared. That means the Lorentz factor of the particles, the typical Lorentz factor of the particles, should be inversely proportional to the cubic root of the magnetic field. The proportionality coefficient is immediately calculated from here. It's called, this magnetic field is called Schwarzschild magnetic field. This is 4 times 10 to 13 Gauss, very large magnetic field. If you take a Gauss scale magnetic field and put 1 Gauss here, you get something like almost 10 to 5. Magically, this corresponds to what we see. It's something like several times 10 to 4. Okay, is it all that you can imagine for this situation? No. I have showed you in the previous lecture, I've shown you that if you try to decrease the Lorentz factor of particles, which are emitting in the synchronous Compton process, then what you get is not just one peak synchrotron and another peak inverse Compton in the classical regime, which will not produce you pairs. Actually, you have another inverse Compton peak, which is going to be in the Klein-Nishina region. Klein-Nishina means that you can produce pairs with these photons. And this is the second order pair balance, which is possible for a source with high opacity. If you have low opacity, then you need many, many target photons. Many target photon means synchron photons. They are the lowest energy. They are the more numerous. If the opacity is very high, you may sustain the same process on the first order inverse Compton photons. So now it's the second order inverse Compton photons that meet the first order inverse Compton photons. And together, they make a pair. So now the condition for the pair production is this one. It's a product of the two inverse Compton energies. And you solve the equation in the same way. And what you get is that the Lorentz factor of injected electrons is 1 over 1/5 power of the magnetic field. So it's a slower dependence on the magnetic field. Moreover, since the magnetic field is very, very low, we can say that this number is roughly 100 times less, more or less. What does it mean? There was a question after the first lecture, why the spectra are different? If it's the same process, why the spectra are different? Because some sources are compact, some sources have very large opacity, and they work with the second order process. That means lower energy of the accelerated electrons, and that means, of course, the low energy of accelerated electrons means that you have lower energy of the synchron photons and lower energy of the inverse Compton photons. So what should characterize this kind of objects? The low energy synchronal peak, the low energy inverse Compton peak, but the inverse Compton peak now, remember, it's two peaks. It's a first order and second order peak. So now the inverse Compton peak should be broader. And it also should be higher. What you do, you maximize, maybe I should go back. You maximize the efficiency of producing the pairs. That means that the powers of the photons that are absorbing and the power of the photons which are being absorbed is roughly the same. It's the power of that goes into pairs is the product of the two. It's like you multiply x times 1 minus x, the energy is divided between the two, and the maximum, if you multiply x by 1 minus x, is the maximum is when x is 1/2. So one half of the energy at the optimal, one half of the energy should be in the low energy absorbing photons, one half of the energy in the high energy absorbed photons. So this means that this height and this height should be approximately the same. I am not saying anything about the height of the synchrotron peak. Why it should be lower? Because the Compton potential is large. Why it's large? It's difficult to explain in few words, but basically it has something to do with the way the particles are being accelerated. The way the particles are being accelerated is because you actually, in the long run, what accelerates particles is the electric field. And the electric field comes into play when you consider the change of the magnetic field. So the particles are being accelerated by the change of the magnetic field in the long run. So if you put energy into the turbulent magnetic field, some part of this energy is channeled to the magnetic field itself and some to the acceleration of particles. When the magnetic field boils in this turbulent pot, it also loses some energy and gives it to the particles. So you accelerate particles, channeling energy to the accelerated particles in two ways, and only one way to channel energy to the magnetic field, so it's less efficient. This is why we have more in the particles than in the fields, more or less. It's very qualitative argument, of course. But anyway, since the Compton potential is high, we can say that the ratio of the synchrotron power to the magnetic field energy density is the same as the ratio of the first peak to the synchrotron peak, because it's in Thomson. It's the same ratio, same cross-section, sigma Thomson. And it's larger than unity, usually much larger than unity. Here, it's a different situation for the first order. It's the same story. The power in the absorbing photons should be approximately equal to the power in the absorbed photons. But then it means that the synchrotron and the inverse Compton peak are of approximately the same height, no matter what's the Compton potential. Why? Because of the Klein-Nishina that brings back the second peak. Here's the same story. The second peak is not higher than the first peak. It's the same level because of the Klein-Nishina. Same story. Okay, now this might be a coincidence that you kind of reproduce the two populations of blazars with a single model. But let's try to think if the pair balance model gives you some specific predictions that you can check. And yes, it gives. Of course, we can only we can consider many predictions, but we are interested in the predictions that are different from the standard diffusive shock acceleration. If it gives you something similar, like that the particle spectrum should be a power law, it's the same. Well, how can you check whether you have one or another? It's roughly the same prediction. Okay, what it tells you, because the shock now is sustained by the secondary pairs, the ones that are being accelerated in the process, this means actually that all the energy goes to the accelerated particles. This is actually good in terms of the energy efficiency of the sources, but it's not so easy to check whether you have 0.1 or 1, because we have no idea what's the actual power in the source. We can speculate. It looks like, yes, it's more easy to do with this than with 0.1, but it's not really something that you can use as a firm argument in favor of one or another theory. Another prediction is that luminosity in absorbing and absorbed photons are approximately the same. Yes, this is what we see, but this is not excluded in the standard model. And the standard model should be a coincidence because there is no reason for that. But it's possible. We have very few objects. I told you that basically this is intended for gamma ray bursts. We have only two well-measured gamma ray bursts, so maybe both of them are just a coincidence. Strange, but happens. Who knows? But then we have yet another prediction that now the Lorentz factor of injected electrons is inversely proportional to the cubic or fifth power root of the magnetic field. As the shock expands, the magnetic field decreases. That means the Lorentz factor of accelerated electrons should increase as the shock expands. So with time, you accelerate particles to higher and higher energy. This is the prediction of the pair bounds. In the standard standalone acceleration process, I told you that from a very, very general energy conservation arguments, you can tell that the typical energy of particles decreases with time because it's proportional to the shock Lorentz factor, and the shock Lorentz factor goes down as the shock decelerates. So it's just the opposite predictions. We should be able to check it. To do that, we need one burst where we have measurements at different time, and we can check what happens. Unfortunately, it's one and only one burst where we can do this in a good way, more or less good way. This is the number of this guy. And what you can do is that for the early first night measurements, it's the measurements why first night and second night, because these are using the observations by TeV Cherenkov telescopes, which you can only observe at night. The first night observations and second night observations. The difference in time between them is large enough to see evolution. And what we try to do is let's constrain in the parameter space, let's constrain the region where the Lorentz factor of accelerated electrons can be. Well, this is a two-dimensional projection of a four-dimensional parameter space. So on other two dimensions, you have done optimization of the parameters. And this is the region that is left, this blue line. Okay, let's try to do the same for the second night. And then there comes a trouble that, yes, you can constrain, but the constraint is, you see, it's very, very vague, I would say. Anyway, what you can do now, let's take this blue line and shift it in two different directions. One way you shift it to reflect the predictions of the standard diffusive shock acceleration, and this is this one, proportional to the gamma. Another way you shift it, and this is inversely proportional to the cubic root of the magnetic field. If I ask you, I think you will agree that this one is in much better agreement with what we see. This is the line that you probably would draw through the center of this region. This is the Lorentz factor of the shock. And you see, this is almost in the middle of the allowed region for the second night. And if you use the standard assumptions, it's outside, more or less. Well, yes, this is one case. Unfortunately, we have no any other case at the moment. And this is not that compelling. It's not 5 sigma that you have in particle physics as a golden standard for discovery. It's not 5 sigma, unfortunately. But you can believe me that in particle physics, why it's 5 sigma? Because you have many, many billions of events, if not more than that. Actually, that means very many trials. You may see very strange things if you have very many trials. In astrophysics, it's not so many trials. So even 2 sigma is quite a good signature that you are right. Anyway, yes, this is the only example. You may speculate whatever you like. If this is correct, what we can do? Of course, we want to put this into a good use, and the good use would be to solve the reverse problem. You have a spectrum. You want to say what are the parameters of the emitting region. Can you do this just looking at the spectrum? Suppose it's a very sketchy spectrum. Like you have a position of the first peak, position of the second peak, and the relative height of the two peaks. Can you tell anything about that, from that? Yes. If you use the first order pair balance, you know what is the product of these energies in the Camoin frame. And what we see now is blue shifted with the Lorentz factor. Oh, this is it. The Lorentz factor is just the square root of the product of the two energies divided by mc squared. Very simple, immediate estimate. The Lorentz factor of injected electrons, how we know that? We know that this is in Klein-Nishina. So this is the energy of the electrons that are scattering photons. The scattered photons in the Klein-Nishina has the energy of the scattering electron. Oh, this is this energy. Okay, multiplied by gamma again. So immediately you get it. What's about the magnetic field? Well, you have the Lorentz factor of an electron, you have the blue shift by the Doppler factor, by the Lorentz factor, and you have the synchrotron frequency here. Oh, it's easy. You immediately estimate the magnetic field. What you cannot estimate from here, you are missing one parameter here, the relative height of the peaks. So the fourth parameter, the Compton potential, cannot be estimated from that. We know that in the first order pair balance, they are always at the same height. So it's the memory of the Compton parameter of the Compton potential is lost. But if you have the second order pair balance, then you can estimate all of them. What's the difficulty here? Again, it's the spectrum is too peaked, apparently. But I told you that the second peak, it should be broader, is actually consisting of two peaks. So this E2 now is not readily visible. It's hidden somewhere. But what we can see is E3, the last peak, and E1, the synchronous peak. So we use this knowledge and calculate in the similar way. We calculate the Lorentz factor of the shock, the Lorentz factor of the emitting region, the Lorentz factor of the accelerated electrons, the magnetic field, just in the same way. And now I told you that the ratio of the second peak to the third peak, they should be equal because of the pair balance. And the ratio of the second peak to the first peak equals to the ratio of the first peak to the energy density of the magnetic field. So the square of this is the Compton potential. From that, you calculate the Compton potential. You know all four of them just from this sketch. Of course, there are numbers here. The devil is in details. The numbers may change your estimate. If you're aiming at exact science, something like plus minus 20, 30%, then of course you cannot do that. You have to take the whole calculation with all these equations that I have shown you and calculate it precisely. But if you want to estimate it quickly, easily, no problem. Then what happens if somebody shows you a two-peak spectrum where one peak is at 1 keV and another one is at 1 MeV? What are you going to tell? You are going to tell you are pulling my leg. It cannot be. Because if you take the product of the two, get a square root, you will get a Lorentz factor which is 1 over 30, less than 1. No, it cannot be. This way, by the way, this is, can be used to distinguish if you don't know exactly. Usually it's kind of obvious which one to use, the first order or the second order process. But if you are not sure, you can try with the first order. If you get a crazy answer, then you can try with the second order. And only if you don't get a normal answer with any order, first order or second order, you may say that no, SSC with pair balance doesn't work. I have never seen a source like that. That's such that SSC with pair balance would not work according to these definitions. But yes, we have to we have to bear in mind that yes, there is at least one example of the spectrum that cannot be reproduced within one zone model. You cannot see it from here, because from here you can derive some parameters, which, by the way, would be reasonable, and probably they are more or less correct, but the exact shape of the spectrum cannot be reproduced still. So this is a very crude estimate, which probably works even in the case when the exact shape of the spectrum is not reproduced. Now, coming to the magnetic fields. What do we know about the magnetic fields? With active galactic nuclei, we know nothing, in the sense that, yes, we can take one instance of an AGN, calculate the parameters, another instance of an AGN, calculate the parameters, but then I told you that there is a degeneracy in the parameter space, so this doesn't give you a good idea of what is the magnetic field, just a very vague estimate like plus minus 1 order of magnitude. Even this will not tell you much because since you don't know where is the emitting region, it doesn't place a really strict constraint on your models. What you can do, take GRBs. There are two GRBs. I told you that for every GRB there was a measurement, one measurement at earlier time and another measurement at later time. So we have 4 measurements with 2 GRBs. And we can place the numbers. Yes, we have to bear in mind that, keep in mind that, yes, these are 2 different GRBs. So in principle, there could be some bias between them. But it looks like a very well-pronounced trend that the magnetization goes down in the shock. Oh, it's not a universal number. It evolves with time. Let's try to find out what we can do with this. And now I go into tell you what, in principle, we think are the processes that are shaping the magnetic field and governing its evolution. First of all, we believe that the magnetic field far upstream is generated by variable instability. Variable instability is the following. You have currents, seed currents of alternating directions, and the alternating currents are they tend to the magnetic field between the currents. It tends to deflect the particles in a way that they join the current similar with their direction. So particles from the sides are joining the currents. If they are joining the currents become stronger, the magnetic field becomes stronger, it deflects particles stronger, so it's a classical instability as it should be. It just supports itself and the magnetic field grows. This is a periodic instability, and the magnetic field in principle can grow up to the point that the gyro radius of particles is of the same order as the correlation length of the magnetic field. Beyond that, you cannot go, obviously, because what you need is you need to deflect particles from between the currents to the current. So the particle has to move from between the currents to the center of the current. That means its gyro radius should be larger. Or otherwise, it will be just stuck in some point. So this is the well-known process, and why we believe that we need such kind of instability. Why not just use an interstellar magnetic field? It's there. It's because if you compress this magnetic field, the interstellar magnetic field, yes, it's compressed by gamma, but even this is not enough to sustain the synchrotron radiation at a level that we see it. So we need to amplify the magnetic field, and the way to amplify it is by instabilities. This is the way. Then, if you consider this instability, the maximum increment is determined by the anisotropy in plasma, some coefficient by the plasma frequency and the energy of particles in the plasma. Let's forget about this gamma to 1/2 for a moment. So it's a plasma frequency times some coefficient, numeric, dimensionless, which we take of the order of unity. So probably at the shocks, the plasma is quite anisotropic. Formally, this coefficient could be much, much larger than unity, but really formally, if you prepare specified initial conditions, specific initial conditions. This corresponds to the wave number, which is this one, and again, it is related to the plasma frequency. Now what you do is that you know at which rate the magnetic field is decaying in the plasma with 0 anisotropy. So isotropic plasma, if you put the magnetic field, it will decay. Not because of the, this is important, not because of the ohmic decay. It's not the ohmic decay, it's kinetic decay. It's because the plasma particles are moving in random directions and they smear out the currents. So the smaller is the region of the magnetic field, the faster it decays. And yes, it's the same for the ohmic decay, but the law is different. So you put into these equations, you plug in this wave number. So once again, you made the magnetic field through the instability. This way you know the typical size of the fluctuations in the magnetic field. You plug this size into here and you calculate the decay time, and you get 1 over gamma here. So the rise time and decay time is the same. If you want to create magnetic field fast, it will decay fast. sounds reasonable, but it's not so obvious. But then you make some numeric estimates. You calculate this quantity, just plugging in some reasonable number. We know what are the parameters of the GRB afterglows, so we plug in some typical numbers, and yes, we get 10 to the minus 6 seconds. I have to remind you that the duration of a GRB itself is 100 seconds. 10 to the minus 6 is much larger than 100 seconds, but okay, you say we have the synchrotron radiation, and maybe it's so fast that even this is enough. Unfortunately, no. This is a much easier exercise. You know the power synchron radiation, then you immediately calculate the lifetime for an electron, the cooling time. You plug in the typical numbers for the GRB afterglow. What you get is tens of seconds. And this is a disaster, because if you divide the magnetic field decay time by the synchronous cooling time, it's a tiny fraction of the synchronous cooling time. If you put an electron in this field, it will radiate synchrotron, but will quit immediately. It will not radiate anything. We know from some specific energy considerations how much energy in principle could be kinetic energy, in principle could be in afterglow shocks. So we know what's the efficiency of the synchronous radiation should be not to violate these energy constraints. And it should be something like 0.1, maybe in some cases 0.01, but definitely not 10 to the minus 6. This is not allowed. So this is a trouble. How to solve this trouble was clear actually a very long time ago. If you cannot sustain the magnetic field for much longer than you generate the magnetic field, what you do is you slow down the generation of the magnetic field. This is actually the natural outcome of the pair balance. Remember, now the width of the shock is determined by the mean free path of a photon, not of an electron, of a photon that is running ahead of the shock. It's a big number. In a plasma scale, it's a very big number. So you inject the pairs all over the way, and since you inject the pairs all over the way, it takes a long time to generate the magnetic field. Well, of course, you cannot reproduce it in numerical simulations because you cannot really reach that large dynamical time scale. What you can do is, say you use the injection which is 10 times slower than usual, more or less, and see what happens. And this is the comparison of what happens. If you have slow injection, you generate the magnetic field in front of the shock, then the shock comes, the magnetic field is getting compressed, and this is what happens. This is the picture of the shock, of the shock-generated magnetic field if you don't have pre-injection. You see, it's a very, very small scale field. I'm not sure if you can even discern from large distance, if you can even discern the different lines of the magnetic field. And what happens if you have pre-injection? You produce some small scale magnetic field here, then you see that the scale is still visible. The initial scale is still visible in this picture. It's inherited from the initial magnetic field. And that way, the magnetic field decays slower. Indeed, this is what we see. The magnetic field decays slower. Unfortunately, the magnetic field also itself has smaller amplitude. Why? Because of the general limitation of the Weibel instability. It cannot operate if the gyro radius of a particle becomes smaller than the size of the magnetic fluctuations. If you just increase the size of the magnetic fluctuations with the same magnetic field, that means your gyro radius should be huge. That means the energy of a particle should be huge, and this is not what we see. So this is a natural outcome. Oh, this was kind of promising answer, but if you look closer, it's not. It still has a problem of its own. Now, let's try to do some magic. This is another second dose of equations. Now, it's not to show you that these equations are too complicated for you to follow. This is to show you that sometimes a magic occurs. You calculate the synchrotron efficiency. This is actually same equation like here. This is the synchrotron efficiency. This is the ratio of the magnetic decay time to the synchron cooling time. You calculate it and rewrite the same equation. I will rewrite it in a slightly different way. Rg, the gyro radius of a particle, was not in the initial equation. I know what's going to be the answer. So I just separate this coefficient, which is lambda c, the correlation length of the magnetic field, divided by Rg times something complicated. And then what I'm going to do is probably the thing that you know as students. This is usually called in an ironic way a method of visual inspection or deep visual inspection. You just stare at the equation until you get an insight, oh, the solution should be like this. I don't know how to see from this equation the outcome that I'm going to show you. But I will just go direct you step by step. There are not so many steps. You just do simple substitutions, and then magically, from the requirement that the synchron efficiency is high, you get the answer. This is a spoiler. You get the answer that the gyro radius of particles should be much smaller than the correlation length of the magnetic field. It's absolutely inobvious conclusion that synchrotron radiation cannot be efficient unless you meet this requirement from the beginning. Anyway, what you do, first step, you calculate the plasma frequency through the gyro frequency. They are related because this one depends on the density of plasma. If you multiply the density of plasma by mc squared, you get the energy density of plasma, and then you can relate the energy density of plasma to the energy density of the magnetic field. And this is one of the parameters that we use in modeling. This is epsilon b. So they are related through epsilon b. Okay, we plug it in here. I do not expect that you follow all the steps, just showing you the steps. The next, we express, well, first we substitute the Thomson cross-section through the fundamental quantities, and then we express the magnetic field through omega b. Again, no way, it's a simple expression, it's just a definition. Then we relate the observable, the energy of a synchrotron photon through the gyro frequency. This is blue shift times gamma squared times h omega b. And we express the gyro radius of a particle through the magnetic, through omega b, through the gyro frequency. We plug it into the equations. This is what you get. Well, you can probably immediately recognize that this is fine structure constant. So in the final answer, it appears. Now, let's look at this expression. First of all, we can say that, okay, this is an observable, this is a fundamental constant, and this is the Shock-Lorentz factor. Well, we cannot measure it really, but we know it from many, many different arguments. We know what's our approximate number for this. So this can be calculated, or at least estimated. What we don't know is the ratio of energy of a typical plasma particle to the energy of radiating particles. It can be, in principle, anything. But then look at here. If you forget about this term that we are going to estimate, you get that the synchron efficiency is less than 10 to the minus 4 times this ratio. But it should be large. It should be no less than 0.01. So one way, okay, maybe this ratio is very, very large. And that would mean that a typical particle in a plasma has energy much, much larger than the typical energy of radiating particles. What it means that very few energy is put into the radiating particles. So even if they are radiating efficiently, the amount of energy which is there is not enough. Oh, this doesn't work. The only way out is that to say that lambda c divided by Rg is a large number. And that means the particles are confined in the magnetic field. The plasma particles, once again, it's a current-bearing particles, the ones that support the magnetic field. They are confined in plasma, and this is impossible for variable instability. And this is consequence from observations, direct consequence from observations, a very simple theoretical exercise. What does it mean? Maybe the magnetic field is created by variable instability, but the acting magnetic field comes from something else, not from variable instability. A very far-fetching conclusion from these simple considerations. Okay, but now we have to change a little bit our argument to see if we are safe that we used one zone SSC model. To be safe, that means let's check if the one zone model in principle can be valid. First of all, let's calculate the ratio of the correlation length of the magnetic field to the gyro radius of emitting particles is large or not. And you get this answer. I'm not going into the details now. You get this answer. So now you have this ratio reversed. So in principle, you can play with this ratio. It can be large, can be small. I will tell you that my choice would probably be that it's not very large. And that means the gyro radius of emitting particles is still smaller than the correlation length of the magnetic field. So the particles, the radiating particles now, not plasma particles, are also confined in the magnetic field. Looks like a trouble, and then you realize that, oh, no, it's not that the magnetic field just keeps the particles in the same place. It's a different story, because the magnetic field is turbulent, the particle wanders, it has so-called Pong diffusion. So it diffuses always from the initial point. What we have to calculate is the diffusion length of particles over the time it takes to radiate synchrotron. And then if you calculate the diffusion length, then this diffusion length is no way, it's much, much larger than the size of the fluctuations of the magnetic field. So one zone model is safe. We can use it. The magnetic field is very non-uniform, this is for sure, but every radiating particle samples all the magnetic field. So it goes from one place to another, losing energy in an average magnetic field. What it can change the average spectrum of a single particle, so of a synchronous spectrum of a single particles, and it probably does. But it cannot break the one zone approximation as such. So we can use it. We came to this conclusion with one zone approximation, and we confirmed that, yes, we can use it. Now, the final part of this talk is the simulations. And let's see if we can take advantage of high technology. Okay. This is a movie. This is an upstream. And you see, this is the shock. This is magnetic field in the plasma, and this is behind the shock. Maybe we can repeat it once again. So what to see now? Fix your sight at some region. In the upstream, it's the same. Now it changes everything in the shock. Now if you go to the downstream, the magnetic field decays, but the geometry of the magnetic field stays the same. So it's just some magnetic field is created, and it stays the same. Yes, can we go back? Yes. So this is the global picture of the magnetic field in the simulation that we have run. This is the upstream. This is the downstream. The magnetic field, yes, it's amplified in the upstream. It's getting some different geometry, spotlight geometry in the downstream. And it decays, actually. You cannot see it right from here. This is the frame sequence of the movie that you have just seen. So one by one, we were going in the Camoin frame, and we saw what happened to the magnetic field. And just to make it more visible, let's average over each frame, let's average along the x direction, along the movement direction, the magnetic field. And you clearly see the traces of the magnetic spots in the upstream, you clearly see the traces of the magnetic spots in the downstream, and you see that they break at the shock. The shock is the reconnection region. The shock is the only place where the geometry of the magnetic field lines really changes. So it increases due to the instability. Now this is the magnetic field, the magnetization as a function of distance to the shock. This is the upstream. Look at the coordinate. This is kind of stretched logarithmic coordinate. So this, close to the zero, it's linear, and this way it's becoming logarithmic. So if you start from here, from the upstream, the magnetic field increases like a power law. In the downstream, it also decreases like a power law. In the between, you see this dashed blue line. The magnetic field looks like it's just being compressed as an MHD. This is a very good approximation, actually. This is just compression, lossless compression of the magnetic field. The magnetic field is being compressed by the fluid itself, by the motion of the fluid. Oh, this is why we have the magnetic field much stronger than the Baikal stability tells you. But once again, this is peak simulations of a normal plasma, no pair balance here, no pair production, nothing. It's just a normal simulation of a plasma. Even then, you see that the magnetic field doesn't really follow the Baikal instability. Close to the shock, it follows a different law. This is the distribution of the magnetic field over the magnetic field strength. So this is the probability that at some distance from the shock, this is closer to the shock, further from the shock, still further, and this one, the furthest from the shock. This is the probability that you will encounter the magnetization like that. You see that this probability is skewed in a way that most of the energy of the magnetic field is actually contained in a very small regions of magnetic spots. Moreover, if you look at the evolution, this one is closer to the shock, the blue one, the magenta one is further from the shock, but you see their peak just coincides. That means the strength of the magnetic field at the centers of the spot is the same. It doesn't decrease. The magnetic field itself, on average, decreases. And this is because of this part of the distribution. And that means what happens to the spots, they shrink in size, but their amplitude stays the same. They are soliton-like solutions. And then just before I conclude, this is a slide which is really a speculation. Because what I was telling you now was based on a two-dimensional simulations. We know that going from 2D to 3D sometimes brings really new physics. So if we can extend it to 3D, and if the evolution of the magnetic field in the downstream stays the same, that means that every particle will eventually radiate in the magnetic field, because the integral of the magnetic field squared over the distance diverges. This integral. Oh, sorry. This one. You see? This is x to the minus 0.8. If you integrate over x, this is divergent. That means every particle will radiate. But the longer you wait, the further away it has to go from the shock, and the smaller will be the magnetic field in this region. This is similar, very similar to what we see from the fits, where the Compton potential, which is actually the reverse, the inverse of the magnetization, is going up with time. The magnetization goes down, and this is probably why. And something has to be changed in our models. This is not yet done. This probably has to be done by you, by me, by someone else. The synchrotron power is becoming very tricky. The synchrotron power is set by epsilon b, but the peak of the synchron emission is set by the local overmagnetized region. It's set by the energy, by the total energy density. These regions, by the way, I didn't tell you, these regions, by the way, have magnetization at the centers, which is not very far from unity, something like 0.3. So it's not the same now. the power is set by the mean magnetic field, and the frequency is set by the highest magnetic field. And they're very different. They can be different by orders of magnitude in principle. No, not orders, 2 orders of magnitude. And in principle, because of this distribution that I have showed you, because of this distribution, you will change the power, the low energy asymptotics in the synchronous spectrum of a single particle. Why it can be that important? Because I didn't show you, but in principle, if you try to model GRBs at a very early time, the model is just perfect. At later time, what you find that the model is perfect everywhere except optical. You underproduce optical. First slightly, then systematically to a higher extent. Or you underproduce optical. It seems that your spectrum that you calculate is too steep in the low energy part. Now, if it changes, this tells you 2 things. First, your model probably better fits the data. And second, it gives you a clue of how the magnetic field really behaves in these relativistic shocks, about the turbulence of the magnetic field. This is the scale that we cannot resolve by any means, only numerically here, but over there we have no idea. Now we have some clue how to handle the situation even without being unable to measure it directly. And yes, this is the summary. Just in a couple of words. The summary is like that. We tried to dive into quite unexplored domain of the microphysics of relativistic shocks and jets to some extent. And doing this, we found that, yes, in principle, acceleration can be joined into a single model. This is a unified model, if you like, kind of electroweak interactions in the particle physics. We can unify particle acceleration and radiation, producing a pair balanced model, which gives you very nice results. But now we have another sector, the magnetic field, which is unexplored sector, and this is kind of great unification, which is yet to be achieved. If you unify all 3 of them, we will get a unified theory of relativistic outflows. Now, we are on the way to do this, but yes, still it's a lot of work. Let's stop here.
Thank you very much. Questions, please?
I have to confess that I'm confused in the end. So you say that Fermi mechanism is kind of not working or not efficient.
Yes, better to say not efficient.
Not
yes.
efficient, yes. Based on the microphysics of different processes, I frankly doubt that if the injected spectrum has some maximum energy, Emax, then after some microphysical processes you can get a larger energy just due to these microphysics processes. I mean, just energy conservation. I mean, what's the physical process which can give you a gain in the energy? So, if my understanding is correct, then anyway you have to rely again on
Yes, the energy conservation is there. Oh, this is the question.
No, it is not.
No?
This is just a part of my comments. And then, I'm just trying to show you my logic. So, if you have some electron plus a photon, or photon plus photon to plus and minus, so on, so you cannot gain, I think, in the end, high energy initially.
Why?
I mean, where you take it.
It's not a closed system. You have a shock. You have kinetic energy of the flow.
So anyway, you rely again on a shock.
Of course.
So what then qualitatively is different in a shock, which you just demonstrated from Fermi shock?
It's still a Fermi acceleration, but a very specific acceleration. What you do in a normal Fermi acceleration is that you just bounce across the shock, scattering particle of the magnetic field fluctuations. And that way you bounce particles. I explained you, I hope that I explained, but at least I tried to explain why it's inefficient in a relativistic setup. this kind of wandering. What you change here is that now you have two scales. One scale for the magnetic field, for the deflection of particle in the magnetic field, which is still short. Another length is for carrying the energy and momentum across the shock, which is done now by photons. They do not care about the magnetic field. So this way you solve the problem that you have to do everything in a very thin region across the shock in just two scattering mean-free paths. You go far away from the shock. You have enough time to isotropize particle to do whatever you like. Then it comes back to the shock, it radiates. You have enough time to radiate. You don't have to bring the particle back to the upstream. It can radiate in the downstream. It should radiate in the downstream. It radiates in the downstream. You produce a photon. It comes back to the upstream. And that way, you are free from any problems which are created by this insufficient scattering of particles. The scattering of particles is always sufficient because you have much, much longer time, which is set by the distance traveled by a photon. Now, this is the difference. But yes, it's Fermi-like process. True. Very specific, but still Fermi-like.
Okay. So, in simple words, what is new? I mean,
in the acceleration,
yes.
Well, two things. One that just I told you, in the sense of kinetics, the new thing is that you use neutral particles to carry energy and momentum, and you use charged particles to change the direction of the momentum. So you do it differently. Neutral particles are good for traveling, charged particles are good for deflection. So you combine both. And about the predictions, since here you rely on the particle creation, on the pair creation by two photons, you know what should be the energy of these two photons to create pairs efficiently. And this gives you immediately the answer, what should be the energy of accelerated particles? Just this. If you don't have this constraint, you have to rely on a general energy conservation laws, as you just said, to try to estimate what should be the energy of particles through the fraction of energy that goes into the particles, fraction of particles that are being accelerated, etc. But once again, anyway, whatever you do, you end up in a situation that because of this energy conservation and the fixed fraction of particles that are being accelerated, the energy of particles goes down as the shock decelerates. This is not what you see. It goes up. Why? Because this condition that sets the energy of particles and not the number of particles. The number of particles goes down dramatically, the number of accelerated particles.
Yeah, still ask one more question. So, we have at least two types of Fermi mechanisms, right? Conventional mechanisms.
Well, much more than that, but yes. Okay, let's
So
keep this.
All of them, as far as I understand, all of them are kind of quite qualitative anyway. So we just we don't have any microphysics inside. So we just different way how we deal the shock wave and how particles are scattered. Can you reformulate what you do here from these micro physical processes in terms of correlations between momenta and so on, say, make a Fermi mechanism type 3, stuff like that. So what, in simple words, how after all this work is done, can we reformulate this in just a couple of equations, how we can get energy gain? What kind of correlations you arrive to?
How we can have an energy gain. I think it even has nothing to do with Fermi acceleration even. It's even simpler. The energy gain is just reflection from a moving wall. Always. It's like that. Then the question is, what's the speed of this moving wall? It's not necessarily, as I told you, there is a precursor, so the speed of the moving wall is not a wall, it's a sequence of walls, and every particle finds its own wall to be reflected, has its own energy gain. If the upstream Lorentz factor is very, very large, then you can solve it analytically in this limit. And then you can get the distribution of particles, the power law in the distribution of particles. This is 2.5, and this what fits the observations nicely. It's not 2.2 that you get from this kind of diffusive shock acceleration for the relativistic shock. It's 2.5. Anyway, it's still a power law. But this power law will break if the Lorentz factor is not high enough. Not high enough is something like 10. And that means that all AGNs are out of this description. And even the late time afterglow is out of this description. So it's a simplified description that gives you a qualitative idea what's going to happen at the late stage. But yes, for the late stage, unfortunately, I think, as usual, we have to solve it numerically. We have to set up the numerical model and try to solve it. And I doubt that it will be a power law at all. Most likely not.
Okay.